So there are two stars. They both have this mass of the sun. So that's 2 times 10 to the 30th. Just and everything's at rest until they pull a comet towards them. So both of them pull the comet towards them, and then basically what we're trying to find is, and this comet's initially at rest. So what we're trying to find is we're going to try to find the velocity at the midpoint between the planets. So because it is not an orbit, we cannot use centrifugal force, but we can describe its change in energy using conservation of energy. So we know that the total energy is going to have to equal 0. So 1 half mv squared. And then this is the mass of the comet minus. And then because both of them are pulling together, I'm just going to combine it to one mass. So 2g m and then sun times mc, and then over r over 2, right? Because it's in the midpoint, which should be 4 when you multiply everything out, or at least 4 on the top. And then all that equals 0. So you can divide MC on both sides, assuming MC is 0, which is not 0, which in this case it isn't. We can have 1 half v squared minus 4g ms over r equal 0. And then you can add 4g ms over r to both sides. So you get 1 half v squared equals 4g ms over r. And then you multiply 2 by both sides, so v squared equals 8g mass of the sum over r. And then you square root it, and you get v equals to the square root of 8g ms over r. And then that would be roughly equal to, hold up, let me write it bigger. $32,668 meters per second. Alright, so here we have another practice problem. So let's just say the Earth just randomly stops and is about 1.5 times 10 to the 11th meters away from the sun. And then because it just randomly stopped, it would no longer be in orbit, and it would just be sucked in by the sun, and then they collide around here, around 7.02 times 10 to the 8th meters away from the distance of the center. So what we're going to try to do is we're going to try to find the final velocity of the Earth. So we know initially it's at rest, but it initially has some distance away from each other. So it would be, and let's just call this R1, and then let's call this R2. So basically, you have there are initially there are R1 meters apart. So and then it's at equilibrium. It's not moving initially. So 1/2 mv squared initially would be 0. But then at the final state, you have some speed, v, what we're trying to find, and then this is the mass of the Earth, and then you have some distance r2 away from the Sun and the Earth. So g ms me over r2. So what I'm going to do is, because all of these have a mass of the Earth, I'm going to just simplify this. So gms over r1 equals 1/2 v squared minus gms over r2. And then I'm going to add gms r2 to the left side, so we get gms r1 plus gms r2. Be careful, these do not cancel out because they have different distances from each other. So equals 1/2 v squared. So what I'm going to do is I'm going to factor negative gms. So negative gms, and I'm going to multiply by 2 at the same time. So negative 2gms equal times 1 over r1 minus 1 over r2 equals v squared. And then when you take the square root of that, you get negative 2 gms and then times 1 over r1 minus 1 over r2, which is equal to v. And then when you plug everything in, that should be equal to around 613,349. So 6, 1, 3, 3, 4, 9 meters per second. Alright, so next we're supposed to find something called the escape speed from the Earth. So let me just draw a representation of that. So like say our rocket's like right here, and then it escapes the Earth's atmosphere. So initially it's at some v. That's what we're trying to solve to be able to escape the atmosphere, and then r is just the radius of the Earth. And then the final velocity is 0, but the distance from Earth is going to infinity, because once you break the Earth's atmosphere, there's nothing stopping you from going forever, never, 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 never. So what we can do is we can use conservation of energy to solve this. So 1/2 mv squared, and then this is just mass of the rocket, minus g mr me over radius of the Earth, and then that equals 1/2 mv squared times 0, 0, and then that equals negative g mr me over infinity. And when I was doing the proof for, I'm trying to prove that the gravitational potential energy is this, we figured out that anything over infinity is just 0. So this whole entire thing equals 0. So mr v squared minus g mr me over re, that is all equal to 0. So what we can do is we can set them equal to each other. So, and we can also cancel out the masses. So 1/2 v squared equals g me re, and then we can multiply by 2 on both sides, so we get v squared equals 2g me re, and then we get v equals square root of 2g me re. So this should be around 11,200 meters per second.